Well, good evening, everyone. And thank you for joining us for this, the second of our Discover Our Universe lecture series from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, or as we call it, KIPAC. I'm Dan Wilkins, an astrophysics research scientist here at KIPAC and the coordinator of our public talk series. You can find out more about our upcoming events and watch any of the talks you've missed on our website at kipac.stanford.edu/discover. Or if you're joining us on YouTube, don't forget to subscribe. This evening, it's my great pleasure to introduce tonight's speaker, the director of KIPAC, Professor Risa Wechsler. Risa is a professor of physics at Stanford University, and her research explores questions about our existence on the largest scales. She is currently playing a leading role in experiments that are mapping out tens of billions of galaxies from the beginnings of the universe 13 billion years ago to the present day. Her research is aimed at understanding how galaxies form and figuring out just what dark matter and dark energy are. Risa is a fellow of the American Physical Society, as well as a former NASA Hubble Fellow, and has written about and discussed science in numerous public venues from Teen Vogue to the BBC. And we're delighted to have Risa here tonight to tell us about tiny galaxies in a dark universe. After the talk, we'll be hosting a Q&A with Risa, and if you have any questions you'd like to ask, we'll be collecting them all through the talk. If you're joining us on Zoom, head down to the bottom of the screen and press the Q&A button, and you can ask your question there. In YouTube, you can put your questions in the chat box, or alternatively, I'll send around a form in the chat if you want to send your questions in that way. But for now, I'll hand over to Risa.
All right, thanks so much, Dan. It's a real pleasure to be able to be doing these public lectures. We know these are strange times for everyone. And it's nice to get a little break and think about bigger things in the universe. So as we kind of think about the universe, I think in the current situation, I'm sure that a lot of us have spent some of the last few months thinking about what if the world were a little bit different? There's lots of ways to ask that question. You could ask, for example, what if I wasn't stuck at home for 3 months? Or what if your life, how would your life have been different if you were born 5,000 years from now or instead of today? Or how would history be different if the continents were at different latitudes? Or getting a little bit bigger, how would life on Earth have developed if the sun was 10% bigger? Well, I get to think about these kinds of possibilities for a living, but instead of our daily lives, do it with the entire universe. What I do is I make models of a universe in a computer, digital universes that have different starting points, universes made of different kinds of different material. And then I compare these models with what we actually see in our universe to figure out what it is made of and how it evolved. In this example that I show here, the two universes started off with different amounts of matter. And so one ended up clumpier than the other. This process of testing models with measurements of the sky has taught us a huge amount about our universe. And one of the strangest things we've learned is that most of the material in it cannot be seen directly. It appears to be made of something that's entirely different than the matter that makes up you and me. And yet without it, the universe as we know it wouldn't exist. Everything we see with telescopes, the stars and the planets and the gas and the dust, it makes up just about 15% of the mass in our universe. The rest of the mass, about 85% of it, doesn't appear to emit or absorb light. So we can't see it with our eyes and we can't see it with telescopes. We can't see it emitting radio waves or microwaves or any other kind of light. But we can tell it's there because of its influence on what we see. It's a little bit like if you wanted to map our planet and what is on it using this picture of the Earth from space at night. You get some clues from where the light is, but there's so much that you can't see, all the way from people to mountain ranges. And you have to infer what is going on from these limited clues. So we call this unseen material dark matter. If you read about science in the news, or if you've come to one of our talks in the past, you might have heard of dark matter. But even if you have heard of it, it probably seems sort of abstract and far away, and maybe even irrelevant to us. But as far as we can tell, this dark matter is all around us right here. Dark matter particles may be going through our bodies right now as we sit in our houses because we are here on Earth, which is spinning around the sun, which is hurtling through our galaxy at about 500,000 miles per hour. But strangely, this dark matter, as it goes through us, it doesn't bump into us. It just goes right through. So this idea is pretty strange, right? Most of the universe is made of something that we can't see and we can't feel. But that doesn't mean that it doesn't matter. What I think the most exciting thing is about dark matter is that it matters so much for us. In fact, I think that we, our planet, our sun, and our entire galaxy likely wouldn't be here if it didn't exist. So how do we know it's there? And what does it have to do with our existence? Well, in order to understand how we got here, one of the things I want to understand is how our own galaxy came to be. This is an image of our galaxy, the Milky Way. This is what it looks like today. This is an image from a space telescope called Gaia, which is mapping out about 1 billion stars in our galaxy, just about 1/100th of the total number of stars in the Milky Way. So it's interesting to think about, what did this galaxy look like 5 billion years ago? Or what will it look like 5 billion years in the future? What about the hundreds of millions of other galaxies that we have already seen with huge surveys of the sky? It's pretty interesting to understand their stories. How did those get there as well? Why are there so many shapes and sizes and colors? And how would their histories be different if the universe had more or less stuff in it, or if it was made of something else? Well, the wonderful thing about these model universes that we build in computers is that they allow us to test these possibilities. So let's go back to the beginning of that story. Let's go back to a time when there wasn't actually any matter at all, just a tiny fraction of a second after the beginning, about 13.8 billion years ago. In this first moment, the universe expanded very fast. And quantum mechanics tells us that matter is being created and destroyed at all times, all throughout the universe. So during that period of early expansion, the universe was expanding so fast that matter that was created couldn't get destroyed. And so we think that during that period, all of the matter came into existence, both the dark matter and the regular matter that you and I are made of. So let's now go to a time just a little bit after this moment. So this is after the moment matter was created. It's after protons and neutrons formed, after hydrogen formed. It's about 400,000 years after the Big Bang. And at this time, the universe was very similar from one region to the next. There was matter everywhere at really hot temperatures because the universe was really dense at this time. It was also really smooth, almost the same everywhere, but not perfectly smooth. So this is an image taken with a space telescope called the Planck satellite. What it's showing is the temperature of the universe in all directions. And it tells us that in some places, it was a little bit hotter and a little bit denser than others. So the spots in this image represent places where there was more or less mass in the very, very early universe. So what happened next? These tiny spots, they got big because of gravity. The universe has been expanding and becoming less dense overall in the last 13.8 billion years. But in those places that were a little bit denser, gravity worked hard. Those places that had a little bit more mass, gravity pulled more and more mass into those regions. So this might seem a little bit abstract and hard to imagine. So let me show you what I'm talking about here. These computer models that I mentioned allow us to test these ideas. And this is an example of one of them. This is a movie that my research group at KIPAC made of what happened to the universe after the earliest moments. In this movie, just like in our universe, most of the matter in the universe is made of dark matter. And what you see as you start out is that matter is almost evenly distributed. But you see those starting places where there was a little bit of extra material. And when you turn gravity on, more and more material gets pulled into those spots. Once you have enough of it in one place, the hydrogen gas that is mixed along with the dark matter starts to separate. and you form stars and you get a very small galaxy. Over time, over billions of years, those small galaxies, they crash into each other and merge and grow to become much larger galaxies like our own galaxy, the Milky Way. In this movie, the dark matter is colored dark, and the yellow regions are the places that we expect galaxies to form. So what happens if you don't have that dark matter? If you don't have that dark matter, you never get big enough clumps. So in order to form stars, you need at least 1 million times the mass of the sun in one dense region. And without dark matter, you never get that much material in one place. So without dark matter, things stay almost as smooth as they were in the beginning. So what you're seeing here is movies of these two universes side by side. In one of them, similar to our own, things appear to get clumpy quickly. That's a universe in which it's pretty easy to form galaxies. In the other one, not much seems to happen. The things that start out like small clumps stay very small. In this universe, the one without a lot of dark matter, you don't get anything that looks like our galaxy or any other galaxy. You don't get the Milky Way, you don't get the sun, and you don't get us. We just couldn't exist in this kind of universe. One of the most interesting things that dark matter does in the universe is to create structures on a wide range of scales. So small things form first, and then they run into other small things to become bigger. And you can see that there's a lot of complicated structure within both galaxies and on much larger scales. This structure can provide clues to what dark matter is and also to how galaxies form. So we think that dark matter is most of the mass in the universe, and we think we wouldn't be here without it. It could be going through us right now, but what is it? Well, we don't really know. We do have some educated guesses, and we have a lot of ideas about how to find out. So some of the ideas are here. Most physicists think that dark matter is a particle, a subatomic particle, which is similar in many ways to the particles we know of, like protons and neutrons and electrons. And whatever it is, it seems to behave just like regular matter does with respect to gravity. But it's different in some ways. It doesn't emit light, it doesn't absorb light, and it goes right through normal matter without noticing. So we're hoping to learn what particle this thing is, including how heavy each one is and whether anything at all happens when it encounters regular matter. So physicists are really creative, and they come up with lots of ideas for what kind of particle it could be. The thing that makes it really hard is that the good ideas for what it might be span a really wide range. So it could be a particle as small as the smallest subatomic particles. It could be as large as the mass of 100 suns. And these interesting names here, warm dark matter, fuzzy dark matter, self-interacting dark matter, are some of the ideas that people have for what dark matter could be. Certainly not all of them. So how do we find out what it is? Well, there's lots of different ways that we might be able to get clues. And lots of different ways that both physicists and astronomers are trying to figure this out. So one of the things that we're trying to do is to look for dark matter using detectors in deep underground mines. So the idea is to search for any sign that dark matter, which passes right through us and the Earth, might bounce off a more dense material and leave behind some trace of its passage. And this is an example of one of the experiments that we're doing at KIPAC called the LZ experiment to detect these particles underground. Another thing we can try to do is actually see it in the sky. The idea is to look for the possibility that dark matter particles might smack into each other and create light when they do that, that we could see with special gamma ray telescopes. This is a telescope that we also built at SLAC called the Fermi Gamma Ray Space Telescope, which has now actually completed its 10th year observing the sky. Another thing we might try to do is make dark matter in labs on Earth. For example, by smashing particles together at very high velocities using the Large Hadron Collider in Switzerland. So unfortunately, so far, all of these ways have taught us mostly about what dark matter isn't. There were very good ideas about for what these particles could be that we would have already seen, and we haven't seen those yet. So we have to keep looking and thinking harder to actually find out what dark matter is. Now, another way to get some clues about what dark matter is by looking at galaxies. And that is the main way that I focus on in my research. So we talked about how our galaxy, and in fact, every galaxy, probably wouldn't be here without the existence of dark matter. So our model universes also make predictions for a bunch of different things about galaxies. That includes how they're distributed, how they move, both internally and with respect to each other, what they look like in the past. And these predictions actually depend on what dark matter is. So we can use measurements of those galaxies to test those predictions and learn more about how much dark matter there is, where it is, and hopefully even what it is. So I'm going to give you 2 examples of these kinds of galaxy measurements. The first is we can use galaxies to actually make maps of where all the matter is in the universe. I'm a part of a survey called the Dark Energy Survey that has made the largest map of the universe so far. The Dark Energy Survey is a large international collaboration, about 400 members, and KIPAC has played a leading role in a lot of the science. So we surveyed about 1/8 of the sky with this telescope, actually after building a new camera for this telescope, the Blanco telescope in Chile. And what we've done, one of the things we've done with those measurements is to make a map. And this map that you see here is using about 100 million galaxies that we have identified and imaged with the Dark Energy Survey over 1/8 of the sky. The weird shape that you see here just happens to be the part of the sky that we looked at. And so what is this image? This image is a map that we made of the light distorted from these 100 million galaxies. The light is distorted by all of the matter, and that's including the dark matter that is between us and those really far away galaxies. The idea is that the gravity of the dark matter is strong enough to bend the path of light, and so it distorts the way far away things look. This is called gravitational lensing, and I think we'll have future lectures at KIPAC that really focus on that exciting topic. So these kinds of maps can tell us about how much dark matter there is. And consistent with previous measurements, we find that there's much more mass in the universe than lights up. Again, about 85% of the mass in the universe has to be dark to explain these maps. Interestingly, we've not only measured how much mass there is, these maps tell us how that mass is distributed over space and also how it evolves over time. Actually, by measuring how it evolves over time, this provides a clue to the nature of something else very interesting called dark energy, which actually makes up most of the energy in the universe. And I'm not going to be able to talk about that much today, but we'll have several future lectures that are devoted to that topic. So remember, in order to figure out what dark matter is, what particle it is, we'd really like to figure out how big that particle is, how fast it moves, and what happens when dark matter and normal matter run into each other. So we're trying to figure out what the whole universe is made of, really on the very largest scales. Interestingly, it turns out that the tiniest galaxies in the universe can provide some of the best clues. So why is that? Well, in order to understand why that might be, let's go back to these model universes. Here are 2 simulated images of the region around a galaxy like the Milky Way. These are images that are quite similar to the ones from the movies I showed earlier. And this shows 2 universes with different kinds of dark matter. In the one on the left, it's a simulation of a universe filled with something called warm dark matter. The dark matter particles travel faster than they do in the one on the right, which is a simulation of a universe which has so-called cold dark matter. So what happens if the particles are moving fast? If the particles are moving really fast, then for the small clumps of dark matter where the gravity isn't strong enough, the particles just keep going instead of settling down. The gravity isn't strong enough to keep those things gravitationally stuck to the center. And so you end up with fewer of those small clumps. Now, those small clumps are needed to form galaxies. And so we'll get fewer of those as well. Some similar things can happen in other cases. For example, if the dark matter particles and the normal material interact, or if they bump into each other a lot. So we expect galaxies to form within a lot of these dark matter clumps as the gas within them starts to cool and form stars. So we should expect that there should be a lot more really small galaxies in the system on the right than there are in the system on the left. So now let's think a little bit more about these tiny galaxies. I want to go back to this picture of the Milky Way. And it turns out that if you look up at the Milky Way in the southern sky, you can actually see a couple of these tiny galaxies. These are actually galaxies that are orbiting our own galaxy. These two that you see, they're called the Magellanic Clouds, although they were known actually since ancient times by indigenous people in Australia and South America and Africa. One of the Aboriginal stories actually says that these two objects in the sky were an old man and woman by the campfire. So these two galaxies are actually systems that are bound to the Milky Way. They have come in, they've been accreted onto the larger system that the Milky Way is embedded within, and they're now orbiting the Milky Way system. Here's another view of those galaxies, just taken by an amateur astronomer. And each of these galaxies is surrounded by a clump of dark matter, right? The stars and gas fall to the center of the clumps of dark matter. And so if we had dark matter vision, then you would see this extended region around the galaxies on the sky. So these two galaxies, the Magellanic Clouds, these are the only ones that are really easy to see. But maybe there's more. Are there more of these small galaxies that orbit the Milky Way? Well, it turns out that in addition to these two, there were about a dozen small galaxies that were identified by astronomers using photographic plates, surveying the whole sky and looking very carefully for these galaxies. But that was all that was known until about 20 years ago. The exciting thing is that in the last 20 years, new surveys have allowed us to discover a lot more of them. So this is one survey that was done, the Sloan Digital Sky Survey, that surveyed about 1/3 of the entire sky. That's the light gray area shown here is the part that was surveyed by the Sloan Digital Sky Survey. And that survey detected 14 new galaxies, really, really tiny galaxies that appear to be within our Milky Way system. It actually discovered about 100 million other galaxies that are much, much farther away. But these very, very tiny ones that are within the Milky Way system, it found 14 of them. And what did it do? So this image went from 12 really rapidly, started increasing. Sloan Digital Sky Survey was on a pretty small telescope, a 2.5-meter telescope. But the thing that it did really for the first time was survey a very large region of the sky with digitized data sets, and then really did algorithmic searches for these kinds of systems. It turns out that these tiny galaxies have so few stars that you actually can't see them very well against the background, and you have to use special filters that look both for overdensities on the sky and also things that have similar colors so that you can tell their distance away from us and tell that there are systems of stars that are nearby. Now, after the Sloan Digital Sky Survey, I told you already about the dark energy survey. It turns out that we can use it not only to look, to understand the properties of dark energy and to make these maps, but we can also use it to look very nearby. And just to give you a sense of the relative scale of these various surveys, your iPhone, if you have a relatively new one, has about 12 megapixels in its camera, and the cameras on these astronomical survey telescopes are kind of similar. They're just a lot larger. So the Sloan Digital Sky Survey, which is now more than 20 years old from when it was built, was about 10 times larger than your iPhone. And the dark energy survey camera was much, much larger and was able to get a larger area of sky, so 520 megapixels. Still quite challenging to identify these dim galaxies, but here's an example. If you look at this image on the left, this is what this star field looks like. There is a galaxy in here, but this galaxy is quite large on the sky, and it has a really small number of stars. And so in order to identify this, you have to you have to identify stars that have the right colors. So with the dark energy survey, we actually had another huge leap in the number of satellites that have been detected. We call these tiny galaxies that orbit the Milky Way, we call them satellites because they're orbiting our own system. And so we found actually 17 with the dark energy survey, and then a handful of other systems with similar surveys of the southern sky. And now between all of these surveys, we've detected about 60 tiny galaxies that are orbiting our own. So we now have this new picture where we have the Milky Way, we have the largest of its satellites, the large and small Magellanic Clouds, and then a whole bunch of new ones. And actually, they're not quite this visible in the real image, and so I've blown them up here just for visualization purposes. The amazing thing about these new tiny galaxies is that they're really, really tiny. So what do I mean by really tiny? Well, the Milky Way has a few 100 billion stars total. The Large Magellanic Cloud has about 1 billion stars. But the smallest of these tiny galaxies have just a few hundred stars. It turns out that they're actually a lot more massive. Their total mass is much larger, but most of that mass is in dark matter. And so despite the fact that they're really tiny, they can be a big clue to what dark matter is, because they're really sensitive to the properties of dark matter and what's going on behind the scenes. So I want to take a closer look at the relationship between the dark matter and the galaxies. In each of these dark matter clumps that we can simulate in a computer and we expect exists in our universe, we expect to have dark matter and then also some gas that's well mixed with the dark matter. Now, some of these clumps of dark matter are actually too small for the gas to cool down and form stars. So it turns out that only some of them light up. So if the image on the left is the image of what we get in the dark matter, we can't actually see that dark matter, and so only the largest ones are going to light up and turn into galaxies. Now, we don't know exactly how that process happens and which ones light up, and that's one of the things that we're trying to find out with these new measurements. But the exciting thing is that with these 60 things that we found so far, and we expect there's probably at least 100 more, if we go back to this picture of these two different kinds of dark matter, you can kind of see right off the bat, just by eye, that then this one on the left may not have enough galaxies. Once we start finding a whole bunch of them, we can start to rule out the idea that that dark matter is moving really fast. Okay, so just based on the existence of the galaxies that we've already detected, we now know that all of the dark matter particles can't be moving as fast as this image on the left. It's also that not much can be happening when they hit normal matter, because if they were, we wouldn't get as many small galaxies as we're seeing. It turns out there's actually a lot of different things that could reduce those numbers, and there's not very many things that can increase them. So when we find these new galaxies, it allows us to rule out a lot of these different ideas. So just going back to these examples of our ideas for dark matter, we now know that it can't move too fast, so it can't be really warm or hot dark matter. It can't be too fuzzy. It can't have too many interactions with normal matter. So those are some of the things that we're learning. We haven't fully ruled out all of these ideas, but we're ruling out bits and pieces of them at a time. Okay, so going back to this image of the Milky Way, one of the things we really want to understand is we want to understand how our Milky Way fits into the bigger picture of the entire universe, including similar galaxies. The Milky Way, of course, it's only one system, and there are some things that we can only measure inside the Milky Way. The tiniest of these tiny galaxies that we've been talking about is an example, because a galaxy that has a few hundred stars, we can really only see it if it's very nearby. If it's far away, it will just be too dim. So there's two ways we have to get more context to the Milky Way, given that we only have this one system. One is to look again at simulations, and the other is to look farther out in the universe at similar galaxies. So here's an example of a simulation that we've specifically chosen to be pretty similar to the Milky Way and to have a similar formation history to our own. So in this movie, what you're going to see is that the Milky Way galaxy is the galaxy in the middle. There's a small galaxy that's going to come in that's analogous to the Large Magellanic Cloud. And then there's actually a third galaxy that's quite similar to another system that was recently discovered by the Gaia satellite, which is a similar kind of galaxy to the LMC, but that came in earlier than the LMC, so it's already been destroyed. So we're going to just watch a movie of this system. So this, again, this is a simulation which was specifically chosen to be sort of similar to the Milky Way. And you can see that satellite galaxy coming in quite early, getting disrupted. And then quite a bit later, this other system comes in that could be analogous to the Large Magellanic Cloud. So these kinds of simulations allow us to get a lot of context, right? With the Milky Way itself, we can't play the movie backwards and forwards, and we can't change various conditions. But with the simulations, we can do that. So we can see what happened in the past. We can see how it got built up. We can also, in these movies, change the nature of dark matter by making the particles move a little bit faster, making them interact a little bit more, those kinds of things, and see how different it is. The next way we have to get context, right, is we can look at similar systems in real data. And so in order to do this, I'm doing a survey. This is in collaboration with Marla Jiha at Yale and Yayuan Mao at Rutgers and several other collaborators. What we're doing is we're doing a survey of about 100 systems that are similar to the Milky Way. So what I'm showing you here is about 30 of these systems. These are the large systems, sort of similar to, they have a similar total number of stars that the Milky Way does. Now, these systems are about 100 million light years away. So that's actually pretty nearby to a cosmologist like myself, who sometimes looks at things, 12 billion light years away. But it's a lot farther away than the tiny systems we saw before that were within the gravitational pull of the Milky Way. So we identify these systems in existing imaging data, and then we have to work really hard to figure out which small galaxies are associated with them. For example, Do they have things that look like the Magellanic Clouds? Do they have things that look like the even dimmer galaxies? So we've been working on this project for several years, and so far we found nearly 200 new smaller galaxies that are around large galaxies like the Milky Way. Each system we're looking for, we're just finding a handful, between 1 and 10 of these systems that are orbiting those larger galaxies. Now, in this image, the ones on the right are the brighter ones that are similar to the Magellanic Clouds, and the ones on the left are the smallest ones we can see at these distances. So discovering these systems really helps us understand the context of our own galaxy and its even smaller systems. This survey is still in progress, but it's already providing insight and helping us characterize how typical the Milky Way and its satellite galaxies are. One of the really interesting findings so far is that a lot of the smaller ones that we see are currently forming stars, while in the Milky Way, most of the galaxies smaller than the Magellanic Clouds have stopped forming new stars. So what about looking forward? In the next few years, we're going to be able to make much more precise maps of the entire sky. And this is going to help us refine our movies of the whole universe and of our own galaxy. One of the most exciting tools we expect to have is the new observatory called the Vera Rubin Observatory. We're building a camera for this observatory at SLAC. It's called the LSST camera. It will be the largest camera ever built. It's about 3.2 gigapixels. And one of our next lectures will focus on this camera specifically and what it will be able to do. We actually, just a couple of weeks ago, got back into the lab, one person at a time, and are starting to get back to building the camera, and we'll be completing that later in the year, and then shipping the camera down to Chile, where this survey will be starting in a couple of years. And it's a really exciting survey. It's going to survey half the sky and take pictures every 3 days of half the sky. So it'll be able to study things all the way from our own solar system to about 13 billion light years away. But one thing we'll be able to do with the LSST camera is to detect new tiny galaxies and their signatures. We expect probably at least 100 new systems within the Milky Way, which will tell us even more about what dark matter is doing. Just to give you a sense of how these images will improve, this is an example of one of the prettiest galaxies that we know of as it was observed by the Sloan Digital Sky Survey. And this is an image of this same part of the sky imaged by the HyperSubPrimeCam survey. So this is not quite yet at the depth of LSST, but it's getting closer. And if you just go back and forth, you can see not only are there tons more galaxies in the background, there's also a whole bunch more structure and things that are at lower surface brightness in this image that give you a lot more detail about what's going on. So imagine having an image like this of half the sky and taking a new image like this every 3 days to build up a movie of what's happening over a 10-year period. So very exciting survey that we're all looking forward to. We don't just have telescopes and surveys in the sky. We have new experiments to look for dark matter in the lab, and we're building new, more sensitive detectors. These are 3 examples of those experiments that we're doing at KIPAC. 2 of them are looking for a kind of cold dark matter called WIMPs, weakly interacting massive particles. And one is looking for a new kind of dark matter particle called the axion, which is actually a particle that's much less massive. And we use a tool that's called the dark matter radio because it works almost like an AM radio to tune for the frequency of the dark matter. So I'm sure you'll hear more about these experiments in future lectures. So I'm going to end there and take questions. I'll just leave you with these really exciting ideas. You know, dark matter is still a really huge mystery, but it's an extremely exciting time to be thinking about it. We have really clear evidence that it exists, all the way from the scale of the tiniest galaxies to how galaxies and clusters move, to the scale of the whole universe. And we're actually able to make maps of where it is and how it makes normal matter behave. We know we need this dark matter to pull galaxies together, and we're also using the smallest galaxies that have been detected to provide clues about what it is. Now, we don't know whether we're actually going to find it and figure out what it is, but there are a lot of possibilities for discovery. And for sure, we're going to learn more about what it's doing and also about what it isn't. I hope, no matter what, that I've convinced you that this exciting mystery is very close to home and might be the key to a new understanding of our place in the universe. Thank you.
Wow, thank you, Risa. You've certainly sparked a lot of enthusiasm in our audience and prompted a lot of questions. So the first question, sort of putting this into the big picture, you talked about these tiny galaxies, but how does our own galaxy stack up compared to all the others in the universe?
Yeah, so the Milky Way is really a pretty typical galaxy. So we think that actually in the grand scheme of things, there are galaxies, there's, as I said, we've already discovered a few 100 million galaxies that we've actually seen. But if we take the deepest images that we've done so far and extrapolate that to the whole universe, we get numbers like a few 100 billion or maybe even up to 1 trillion as the total number of galaxies in the universe. Now, many of those are very small. There's more small galaxies than there are large galaxies, lots more small galaxies. But the Milky Way is sort of, if you were a typical star in the universe and you asked, if I'm a random star, what kind of galaxy am I going to live in? It would be roughly the Milky Way, roughly the size and mass of the Milky Way. There are galaxies that are about 100 times larger than the Milky Way. There's nothing that's much larger than that. And as I said, these tiny galaxies are quite dramatically smaller than the Milky Way, maybe by even as much as 1 billion times.
Okay, sure. So following up on that, then where would you draw the cutoff between these tiny galaxies and the more average ones like our Milky Way?
Yeah, I mean, it is really a continuum. There's no magic special mass but there are differences. So so one thing that happens is that typical galaxies like the Milky Way, things that are the total brightness of the Milky Way actually come in a really wide range of shapes and sizes. They are red, they are blue, some are star forming, some are not. Some look really elliptical, some look like these really big spirals. With smaller galaxies, we don't get quite as much structure. Actually, the image that I have as my background here is about these, about 100 of these systems that we discovered in the Saga survey. And so you can actually see that on the brighter end here, there's a little bit more diversity in how they look. Yeah. Some are red and blue, whereas as I go down to the dimmer end, they're kind of just like little puffy blobs. So that's maybe one place you could draw a little bit of a line. We call these dwarf galaxies. And these aren't even the tiniest ones. The tiniest ones are even smaller than that. Right?
Mm. And in those dwarf galaxies, then you don't see the normal variety of the galactic shapes, the spirals and the elliptical.
Yeah, they tend to be just like little puffy things. They haven't, they actually, many of them start forming their stars quite early, but they're sort of a little bit more sporadic. They kind of just piddle along after that.
Mm. So do these tiny galaxies have black holes at their centers?
Oh, that's a great question. So again, so black holes are generally thought to live in every galaxy that's large enough. And we don't quite know what enough is yet. So there are systems that are roughly the size of the Magellanic Clouds, that we think can form a black hole. I think in these smaller ones, there's no evidence yet that they have black holes, but we can't yet tell whether they really don't have them or they're just too small to be seen. Okay. And actually, I should say, when I was talking about black holes, I'm talking about the massive black holes that are at the centers of galaxies. Every galaxy has sort of other kinds of black holes that are more like the mass of one star or a few stars rather than, you know, many millions of times the mass of the sun.
Okay. So from the surveys that you've been doing, do you find a connection between the structure of the big galaxy in the middle and how many satellites it's got, or is it more of a random process deciding how the satellites get?
Yeah, that's a really great question. And it's actually one of the big reasons that we started this later survey that I mentioned called the Saga survey, because that was really not well answered yet. So we're just starting to scratch the surface, because before we started this survey, we only knew about the most massive satellites in these kinds of systems. And there seems to be some relation there. So like redder big galaxies seem to have redder small galaxies orbiting them, and vice versa with bluer galaxies. We're just starting to learn now, as we start to build up statistics on these small ones, whether that continues to be true. So it's a big open question, and one that really drove what we're really looking at.
Yeah, and I guess a lot to look forward to with the Vera Rubin Observatory and the next.
Oh, absolutely. We're really going to get a lot more data on these things going forward.
So as you might expect, we've had a lot of questions about dark matter and dark energy. So I guess the first one, at the beginning, you showed this visualization of dark matter, and it was arranged into this almost spider's web of filaments. Mm-hmm. Is there scientific evidence that backs up this type of representation, or is it just an artist's representation?
Yeah, that's a great question. And I don't have an image of that in this talk, but maybe someone else who does a future talk, or me who does a future talk, will show you that evidence more clearly. We actually have beautiful evidence that this really works and that this is really what's going on in the universe. So let's talk about what is that evidence. So we can't see the dark matter directly, but there are two things we can do. The first is we can use galaxies to trace out the dark matter. And we now have galaxy surveys that are dense enough that you can actually sort of start to see that filamentary or spider web kind of pattern that you expect from the dark matter. And when it's not quite as pronounced in the galaxies because you don't have the in-between stuff, right? But it looks very similar, and it looks almost identical to what we predict in these simulations. That's actually the main thing that gives us confidence that we're on the right track with these simulations, is because when we do make predictions for really large numbers of galaxies, and that's also something I work on quite a bit, but I didn't talk about today, we do see that the distribution of galaxies in our models looks very similar to what we actually observe. One of the things I'm really excited about is another survey that I didn't talk about today, called the DESI survey, Dark Energy Spectroscopic Instrument. We just started taking data right before we had to shut down the telescope due to COVID, but it'll come back again soon. And that survey is going to be actually mapping out the 3D positions of galaxies, about 30 million galaxies compared to Sloan, which did 2 or 3 million. So we're going to have about a factor of 10 more. It's going to be much denser, and we expect to really be able to see that filamentary structure much better than we have before. So it's very exciting. There's the second tool that I just mentioned briefly, which is those maps of the mass. And that's done using surveys like the Dark Energy Survey and LSST with the Vera Rubin Observatory, that actually allows you to map out where the mass is. And it doesn't look quite as filamentary because it's fuzzy. It gets fuzzy because of the errors. But actually, again, if you take those simulations and you sort of run them through the errors that you expect, from the observations, you get something that looks almost identical. And it's a really precise test of the models.
So sort of going deeper on that, so zooming into the filaments and the galaxies in the middle of those filaments. And we had a question as to why in the galaxies does the dark matter tend to form this halo around the outside instead of clumping up in the same way that the normal material that makes the stars.
Yes, fantastic question. So the big difference between dark matter and normal matter, so for these purposes, normal matter, let's think of it as being gas particles. It's mostly hydrogen gas, okay? So the key difference between dark matter particles and hydrogen gas particles is that when gas particles hit each other, basically they lose energy. And because they lose energy, if they're moving fast, they lose a little bit and they slow down. And because they slow down, they start to sink to the center, right? So they turn some of their kinetic energy into potential energy, and they sink into the center of those dark matter clumps. Dark matter is different. When it doesn't hit each other, or if it does hit each other, nothing happens. So it doesn't lose that energy. And so it basically just keeps going and it doesn't sink to the center.
Okay, so there's nothing then that takes its energy away.
Exactly. Yep.
Okay, so with these ideas of dark matter and something, all these theories for these different types of particle and field and other phenomena that could make it, how much weight is there still behind theories that dark matter and dark energy, for that matter, of a manifestation of some weird interaction of normal matter or something that we don't quite explain in our theory of gravity properly?
Yeah, well, I'll be honest, it's really hard to rule out all of those models all the way, but I don't, for dark matter, it's also very hard to make them work. So one of the reasons that we're really confident that this idea of dark matter is correct and that it's not just some change in the gravitational law is because of the number of predictions it makes. So a whole bunch of different things. So number one is that image that I showed of the very early universe, the cosmic microwave background. We have no way to explain that image. Even before we get to galaxies, we have no way to explain that image without dark matter. That image alone is a very, very strong measurement of the existence of dark matter that's made of something different than gas and stars and dust. Okay, so that's one. Then, as I said, there's all of these other predictions that it makes. The kinds of simulations that I showed in this talk are really based on the fundamental idea that dark matter is a different kind of particle that behaves the same with respect to gravity, but different with respect to how it emits or absorbs light. And in some ways, it seems really weird, but there's lots of particle physics ideas that would predict such a kind of particle that would behave the same gravitationally and would have different interactions with light. And so those kinds of models make lots of predictions. The tiny galaxies that I talked about today are one of, I think, the most really exciting predictions that model makes. And we weren't sure if they were going to be there. For a long time, people talked about something called the missing satellites problem because we hadn't found them. And now we're finding them. And they are essentially exactly what we expect, modulo this uncertainty of which of these small things are able to form, form stars or not.
Mm. So there's a lot of interest as well in the computers and the movies that you showed them. Those really beautiful movies. How quickly would you say that our knowledge of galaxies and dark matter and the structure of our universe has advanced since supercomputers became available compared to what was done before that?
Yeah, I mean, it's been dramatic. I think one of it turns out actually before we had computers, the very first simulation of something like this, of how a galaxy moved, was actually done with light bulbs. So the idea is that the gravitational force law has the same radial dependence as how light falls off. And so there was an experiment done with about 100 light bulbs that were moved around based on the intensity of light.
Okay.
The first computer models started with, a few hundred particles on fairly small computers. Now we're doing things that are 1 trillion or 10 trillion particles sometimes. So these are run on the largest supercomputers that exist. We try as much as possible to use very large fractions of the machine so we can get them done quickly. The kinds of things that I showed you today, they're a range. They range from things that we do on our own systems, at KIPAC, to things that we do on these really massive national systems. But to the original question about how fast things have progressed, I mean, our computational tools have, of course, progressed along with the development of the computation itself. I think one of the it's actually hard to answer that question about how much we've learned from the computers, partially because one of the most exciting things I think about cosmology and astronomy over the last 30 years is that it's really been a very tight coupling between the observations and the theory and the simulations. That, we're able to simulate something and maybe we didn't see it yet. And then we are able to, build new detectors that we're able to measure things better. And so then we're able to test those models better. So we have this wonderful interplay between making predictions, testing predictions, then being able to make better predictions, then being able to do better tests. And so I think that's why we have made such quick progress. It's been a very exciting field. When I got into this field, when I was in graduate school, we didn't know the answers to these really basic questions. How much dark matter is there? How much dark energy is there? We didn't know those numbers by almost a factor of 10. And now we're measuring them to like the 1% level. So it's been an incredible amount of progress. And these kinds of simulations have been at the heart of our ability to make predictions for what we expect for a given model.
And would you mind saying a little more about these simulations? So, we had some interest in how the simulations are created, how long they take to run, and then how long you spend analyzing them once they're done.
Yeah. So the basic idea of how these simulations are run, all the ones I showed you here are actually, in some sense, they're pretty simple because I only showed you simulations that have just dark matter. And the reason that's simpler is because then we are only calculating the effects of gravity. We're not doing the full, everything that happens in galaxy formation, for example, includes the hydrodynamics of the gas, which cools and then forms stars, and then the stars explode, and then it get more energy into the gas, and then it heats up and cools down again. So it can be quite computationally intensive. Even these simpler ones, we do these because we want to resolve as much of the universe as we can, but also with as fine resolution as we can. So we're always playing a delicate balance between how the resolution that we can get and the volume that we can simulate. And so we do different things depending on what problem we're interested in. We basically think about, what do I need to solve this problem? What kind of computer can I get my hands on right now? But the basic idea is, in a given amount of the universe, we know what is the density of dark matter. So how much mass per unit volume is there? And then we split that mass into a bunch of little particles. And we call them n-body simulations because it's just n particles where n, in the small case might be 100,000 now, in the large case might be 1 trillion. And those are just identical things, and all we're doing is simulating what the gravity does to those particles. So if you start out with a little bit over here, you'll get more when gravity happens, and you saw how that happens. Again, because we do a bunch of different kinds of things, sometimes, the largest of these things can take a few months on really, really massive supercomputers. sometimes we do them on the systems we have locally, and they can take a day or they can take a few months. And the analysis, it kind of depends. Again, sometimes we do a really big simulation on a large computer, and then we spend maybe 5 years analyzing it in different aspects before we, get that amount of time again and do it again. But we do a lot of smaller ones that allow us to be more flexible and then simulate different kinds of things, like different amounts of dark matter, different kind of dark energy, different kind of dark matter. And because we want to try all of these different things, we don't always want to do the biggest simulation because we want to try a bunch of smaller things.
Yeah, so you're sort of focusing on the specific questions sometimes, rather than trying to do everything.
Exactly.
So we had a question just come in. That if a galaxy like our Milky Way is gathering all these smaller galaxies, do those galaxies eventually get swallowed by the Milky Way? And is it possible that a galaxy could ever swallow too many galaxies and it could start going wrong somehow?
Okay, great question. Yes, so this is what happens in the whole history of our universe, is that galaxies merge. Usually if they're two sort of similar size galaxies, you might not think of one swallowing the other, but most of these mergers are one being a lot larger than the other, right? And so if you take a galaxy like the Milky Way, we think that has had a bunch of things come into it in the past, and there's a lot of signs of that. I mentioned one of them, that Gaia Enceladus that was recently discovered. So that was a small galaxy that we think was accreted onto the Milky Way many billions of years ago, and got accreted, spun around, and left a trail behind it of stars in the sky that we can then see, and we can actually trace the path of how it got destroyed. And this one actually was then eventually totally destroyed. There's another galaxy called Sagittarius, which has this stream, but we can still see the galaxy. And so then you have a galaxy like the LMC, which actually we think was accreted quite recently. These Magellanic Clouds, we think they probably only came in maybe 1 or 2 billion years ago compared to the almost 14 billion year history. So in universe time, that's pretty recent. Now you asked if it eats too many of them, does something bad happen? Mostly no. Mostly it just gets more stars.
Okay.
The stars in galaxies are actually very, very far apart from each other. So when two galaxies collide, generally their stars don't collide. It would be very, very rare for stars to collide in a galaxy collision, because in a galaxy, it's like some stars and a lot of space in between. So the galaxies get a little messed up when that happens. Like if you had a really nice spiral and it hits at something else, the spiral gets disturbed and distorted and sometimes turns into an elliptical. But nothing else really bad happens.
So for the most part, those galaxies that collided with us, they just became part of our galaxy.
That's right. That's right.
So we're almost out of time, but I've just got one more question, if you wouldn't mind. So over the next 10 years, what breakthrough are you most looking forward to?
Well, if I could choose anything that we might discover, I would definitely hope to learn what dark matter is. I think it's definitely not guaranteed that will happen, but we have a lot of ways to get clues, right? It could be that we'll see something really definitive in some of these surveys. It could be that we will see something definitive in one of these underground experiments. There's a lot of kinds of dark matter that were not previously that we weren't previously able to detect, that in the next 10 years we will be able to detect. So if I had to pick one, that would be it, but that one's definitely not guaranteed. And there's a whole bunch of other things that I think are guaranteed, that we really, we are guaranteed to discover a lot of new galaxies. We're guaranteed to be able to test, how they're forming. We know for sure we're going to get much, much more precise idea of how the universe is expanding, how it was slowing down and now speeding up. We know we're going to get much more precise measurements of those things. So I think we've got a pretty good decade ahead of us.
Oh, fantastic. I, for one, can't wait. Well, thank you, Risa, and thank you, everyone, for joining us tonight and for sending in all your questions. And we really hope you have enjoyed our lecture. If you'd like to see this or any of our past lectures again, they're all recorded over on our YouTube channel. Just type KIPAC into YouTube and it'll find it. But for now, we'll be back in 2 weeks on Tuesday, June 30th, when actually I'll be talking a little bit about my own research into supermassive black holes, those monsters that are lurking in the hearts of galaxies. So if you want to find out more about that, visit us over on our website, kipac.stanford.edu/discover, or subscribe to our mailing list on that site, or subscribe to our YouTube channel. But thanks for joining us, everyone. Thank you, Risa, and bye-bye for now.
Thank you so much. Thanks, everyone.